Thank you very much. Thank you for being here, and also appreciate the organizer to give me the opportunity to talk my research. So today my talk is iROP. So basically I will go through a bunch of code reuse techniques. So I assume people understand what's a ROP. I just quickly skip the basic stuff and introduce the advanced research part. So my name is Xiaoning Li. I'm from Intel. So I'm the security research and architect in Interlabs. So we deliver lots of products, include the deep safe, some couple new CPU features like VMFunk, HashVE, and also our big team delivers the SGX. So I focus on analyzing and detecting prevention of 0-day. So advanced persistent attack, this kind of stuff, with latest new CPU feature. So I did some research for PatchGuard a couple years ago, talk how to detect the PatchGuard with the PatchGuard decoder. So we have the white paper published at that time, and also I present at a couple conferences before. So now we talk about the return-oriented programming. So I assume lots of people already know that because this is pretty popular content for research for many years, right? So I will go through the basic stuff. Then I will talk about the branch transfer instruction. After that, I will talk a little bit couple different ROP defense mechanisms and how to bypass that with different gadgets. So, and I also will talk about a little bit for some valid gadgets and also some powerful gadgets from the Wall64 by design. So ROP is a popular topic for many years. So I just list a couple references here. So if you want to understand more basic stuff, you can read the content here. So that's a couple talks from different research. That's all very excellent topic. So here, I want to introduce some information here about the real ROP Explorer in APT. So ROP is very popular, right? So we saw lots of ROP-based Explorer. But I want to mention this one because this one is special because in 2 years ago, actually, so there was one PDF 0-day, actually includes 2 vulnerabilities within one single file. So this one is the 0-day was detected by file. They report by file. So this one is very interesting because they only use ROP gadget without shellcode. So that's something we didn't see before. Because usually we talk about ROP gadget, we see how to use the ROP gadget to deliver next stage attack, for example, enable the shellcode, this kind of thing. Right? But this attack is very obfuscated. They use pure ROP gadget to replace the shellcode. They don't need shellcode. Then eventually just run the malware directly. So here is the example for ROP gadget. On stack parroting part. So you can see the left side is the first vulnerability used by this 0-day. They will trigger the ROP gadget to the stack parroting. Like here, when the indirect call happens, they call into here. They push the EX and pop the ESP. That's exactly the way to do the stack parroting. So they have another Explorer to targeting sandbox bypass 0-day. So they use another gadget here to call EX and do very similar thing, push EDX and pop ESP. So this is the way people use a ROP gadget to do the stack parroting. Of course, this attack has lots of gadgets. If you want to understand more, you can search online. Lots of people publish the details. So today, the topic we want to discuss is the ROP gadget is the way to only way to do that, Of course not, because you can see people did a lot of research. The return-oriented programming, just one of the way to deliver real code, right? You can do the return-based, you can do the jump-based, and also you can do call-based, right? So basically that's the concept for drop and call. I also list the reference here. That's 2 papers discuss this kind of attack. So let's think about the return, call, and the jump. They all the approach to real code, right? But if we think about the real code from the branch transfer perspective, so we can find actually we have lots of different combination or different approach to do the branch transfer, do the ROP real code based on the branch transfer. For example, here we know we have the return, right? Actually, we have near return and we have far return. For jump, that's very similar. We have the conditional jump. Then we have the near jump, far jump. Of course, we have the direct jump and the indirect jump. So usually the vulnerability happens with the indirect jump. And also we have the call. We have the near call and the far call, indirect call, direct call. So the indirect call usually is the problem for some vulnerability. Sometimes the vulnerability happens due to this kind of instruction. And beyond that, we also have the interrupt return. This is a very different one. We will talk about later. So we can use the indirect return to some very cool stuff. So return is very straightforward. You can see here. So basically, we have near return and the far return. The near return used like many times in the ROP gadget. We can do the segment inside return, right? So the far return concept happens when you talk about different mode. You want to switch the segment. So I will discuss later. We have lots of slides cover the return or gadget in Wall 64, the Windows 32 on a Windows 64-bit mode. That's the compatibility mode to run the 32-bit application on 64-bit Windows. So for jump, we have the conditional jump. We have lots of conditional jump, right? So basically, this one can be used to construct the long gadget. So that means you can have some gadget linked by conditional jump. So if you inspect the gadget from the starting point, that will be very long gadget. So we also have the near jump and the far jump. The far jump also can be used to switch the segment. We of course, we have call, indirect call, the near call and the far call. The far call also can be used to switch the segment. So erent. So this is an interesting one because you know usually erent will be used by kernel space after you handle the user space call. Then you can use erent return for syscall. And of course, when the interrupt happen or some exception happen, the routine in kernel space also need return to user space with erent. So the erent will automatically switch the CS, the code segment, because you have to return to range 3. So the code segment will include the privilege. So you have to recover to the user space privilege. So when the interrupt happens, for example, if interrupt happens, when the interrupt happens, the CPU will push a bunch of things on stack. For example, current SS, ESP, eFlag, CS, EIP, and error code. So for 32-bit and 32 emulation bit, so only the privilege change, they will push all kinds of information. Otherwise, they just push the flag and the CS, EIP, and the error code. But on 64-bit, they always push SS, ESP, eFlag, CS, EIP, and the error code if they have. So now we talk about the ROP defense and the bypass part. So we have lots of defense already been there, and also some coming. So for example, a couple years ago, people did some research for KBouncer, try to use KBouncer to detect the ROP. And also a couple people used PMU, used the mispredict, this kind of thing, to identify the ROP attack. And of course, the latest Windows already includes the CFG, the control flow guard. That's in the Microsoft release already. And also some research published some topic for hardware assistant CFI, so control flow integrity, and also some shadow stack, this kind of thing. So let's talk about a couple different defense part, and we can discuss the bypass. So first thing we want to discuss is the KBouncer. So KBouncer is the winner of the first Blue Hat prize a couple years ago. So it's also the first one to publicly use LBR, the last branch record. So that's the bunch of information in inter-CPU can help you get the latest the branch record information. Based on that, you can check the ROP policy, this kind of thing. And also this one mentions the policy about the call-preceded gadget. So that means if you do return to arbitrary place, they will block. They will detect that as the attack, because think about usually once the call happens, call instruction will push the return address on the stack. The address will be the call next instruction. So when the return happens, it should land into the next call-preceded instruction, right? So that's very basic policy. And also KBouncer uses the long sequence of the short gadget. So that's very interesting. They assume the gadget, the ROP gadget, should be short. That's very basic idea. So here I list the graph from their paper. So the idea basically is every time when you call into the critical API, for example, virtual protect, so they will do the LBR check, and they do a bunch of policy check, right? So that's the way the KBouncer do the ROP defense. So because KBouncer really rely on three parts. So first is LBR, second is the call procedure policy, third one is the short gadget. So let's talk about LBR firstly. So LBR is some MSR in inter-CPU. So basically you can enable LBR with debug control MSR. Then use the LBR select MSR to select what kind of record you want. For example, you only want to monitor Rin3, so probably you want to disable Rin0 part. So this bit you can set as 1. If you don't want to record the GCC, the conditional jump, you can put the GCC B2 as 1. So basically that's up to user to configure the LBR. Then eventually the LBR register in MSR will keep the all data you want. Of course, we have some limitation because we cannot keep lots of resource for LBR. So based on architecture, we keep up to maybe today up to 32 or 16 MSRs. So here is the MSR you can use to read the LBR data. So basically, from address is when the branch happens, what's the from address, and what's the to address. And the tops is because the CPU will keep changing the LBR. So the tops as the index. So you will know with tops you will know what's the latest LBR record, and you can reverse back to get a couple different logs. So the basic idea to bypass KBouncer here is the LBR history flash. So this one is exactly idea from Nicholas. So Nicholas from UC Berkeley published the paper about this kind of research. So he used a couple different ways to bypass the LVR with the history flash. So here he lists a couple different gadgets. For example, if he use a bunch of jump and return, this kind of thing. So they could to flash the LVR with the logic after you did real stuff. So that means you did some critical part, then you use lots of gadgets to flash the LVR because we only keep limited numbers. So then you just flash. So they cannot get the record, some record related to the critical part. So and also he published a couple different ways. Another way is switch the context based. So here is, for example, here like a big loop like that. So because LVR is cross some resource cross all process. So that means if you do some looping or something like that, then other process could be scheduled. At that time, they also will make the LVR record as latest one. So that means all records will belong to another process. So that's also one way to do the LVR flash. And also he mentioned a couple different ways. So I suggest people can read his paper later to understand more approach. So we discussed a couple different ways to do the LVR flash. So we will focus on this kind of new approach. So first thing is here, if LVR during the setting, LVR setting, you enable call-based approach. So then we have this kind of valid gadget in existing software to cause the call. So for example, if some vulnerability happen and you can control the EX as the special number here, the address here. So you return to this instruction. So this one will call the ESP plus 3C. So look at this stack. If the 3C point to the default, then the code will call into default. So the default code has the immediately indirect branch EX. Because the EX controlled by attacker, so this one point to the 22F2, for example here. So they call him back, right? So you can do lots of loop for this one. Of course, during this cop-based approach, the stack will push, right? So eventually, you can control the ESP plus 3C point to the virtual protect, for example. Then you call into virtual protect. So with this approach, you see if the cop cached by LVR, you can flash LVR, right? If not caused by LVR, you just call into the LVR with the cop-based cop-based gadget. So and also you can flash LVR probably with erent. So the erent is something different, right? Because erent worked for interrupt-based routine usually. So the interrupt could happen at any time. So you don't have rule, right? Return, you can clearly say return should return to call-preceded instruction, right? But for erent, that could be, the interrupts could happen at any place. You cannot control, right? So you can do this kind of thing. If LVR records the erent, then you can do lots of erent-based flash. So LVR gone. If didn't, you can directly use the erent gadget. So the LVR will not catch that if you didn't enable. So that's some new part. So because today people talk a lot for ROP and maybe drop and cop, but I didn't see people use the erent-based gadget yet. So this one will be very powerful in future. And also, like we mentioned previously, we can use the call procedure gadget to the LVR flash, right? So for example, very similar code here. We have the EX AR equals 0. If some vulnerability happen, return or somehow goes the address 22F2. At that time, we keep the stack as left side like this. So we do the indirect call with EXP plus 3C. So this one point to the nally. For example, this one point to the nally A2. So the 98.2 will change the stack, because during this push, and call, you have 3 value on stack. So this one adjust the ESP. So adjust the ESP and then point to the stack you can control. Then after that, you do return. The return can return to call set. That means the call next instruction, right? So like this. Then the ESP can continue +8, and they will check the AL. So if AL equals 0, they can continue. So with this kind of approach, you just flush the LBR with valid gadget, right? The return only happens on call-preceded instruction. So you can easily bypass the policy, right? So that means today people still can use call-preceded gadget to deliver enough attack. So actually, Nicholas from the UC Berkeley and Lucas from the Germany also published 2 different papers talk about this kind of issue. So the valid gadget is enough to deliver the attack. So beyond the LBR-based approach, people also used the branch-based approach, branch mispartition approach. Cross-Strat people published the return mispartition approach on Sandy Bridge a couple years ago on SysCon 2013, I think. So, and I also did some research for indirect call, indirect jump-based mispredict. So basically, the idea is if CPU keep the PMU running, so monitor the performance. PMU is the performance monitor event unit. So in case people don't know that, so you can set the configure the PMU to catch the mispredict event. So for return mispredict based event, that's discussed by cross-Strat people a couple years ago. So you know the return just return. If you use erent, probably you cannot detect that because you have to configure the PMU, and the PMU have to support this kind of thing. And the very different thing for erent is interrupt happen at arbitrary place. How do you know this one is mispredict or not, right? Probably with the erent-based gadget, you can bypass, right? And also you can you have a couple different approach to bypass mispredict. For example, you do the indirect call, you run the gadget and return. That's all follow the rule. You just return to expected place, so the return mispredict never happen, right? So if you do this kind of loop, you also can finish the code reuse. Of course, that really depends on the vulnerability and how many gadgets you need. If 1 or 2 or 3 gadgets enough, probably you can figure out this kind of gadget valid approach to deliver the attack. And also you can use drop, because return mispredict just focus on return. You can use drop to deliver the drop gadget. So, and also you can use the call drop combined gadget to deliver attack. For example, here the indirect call calling to gadget and return to the indirect jump and change to another gadget. So, and also you can do the indirect call and the indirect jump and the gadget. For example, here. So you can use the valid gadget here. If you call into this instruction, if the EDX is controlled, EX control EX no, and the EDX control, then they can jump to EDX. If the EDX, for example, jump to here, then you can just directly copy the forward byte from the EX to the argument 1, right? So you can do this kind of thing. It will never trigger the return mispredict because that's all follows the rule. If call and push the return address on stack, and if return landing to the expected address. So, and also for indirect call, indirect jump based mispredict, you can use a couple different way to avoid the mispredict. Sometimes that's really depends on the risk condition. So for control flow guard, because we have limited time, so I will not discuss too much. So basically, the control flow guard is the approach from Microsoft. Every time you do the indirect call, they will check the indirect call to make sure the indirect call landing to the right address belong to the function. Otherwise, they will block. So a couple of people published the research here, and also this year one Black Hat topic about control flow guard. So I suggest you can read the reference. And also for hardware-based control flow integrity, the approach is today we can do arbitrary return write call and jump, right? So eventually it's possible CPU provides the capability, say, hardware provides the capability, say, you only can land into some place with the safe tag. For example, if you return, you should return to some place to indicate this is the place, allow return. Otherwise, you will get failure, right? So this paper published by Lucas talk about the hardware enhanced ROP defense. So basically, the thing here is think about the policy. If you have to land into the place with tag, that means that that's always valid gadget, right? They try to stop the unintended gadget. So for example, return to the call-preceded instruction. The call calling to the function entry, the jump calling to the place should be the landing with the call label, this kind of thing. So that's all belong to valid gadget. That means in future, if we have this kind of capability, you have to use the valid gadget to initiate the attack. Otherwise, it doesn't work, right? So today, if you look at the real attacks, that's all almost based on unintended gadget. So and another approach could be used to defend ROP is the shadow stack. That means every time the call happens, it puts the value on the stack, shadow stack, and when return happens, they check that and make sure that's matched. So that's pretty much very close to the return miss predict, because actually in return miss in current CPU they have limited buffer for shadow stack, very similar stuff. So but if people do this kind of thing, then that means you also rely on the valid gadget. You only can use valid gadget to do the attack. So now we talk a little bit about the valid gadget here. So first thing I want to discuss is stack parity. So we saw the case here. They use the unintended code to the stack parity, right? So we will show how to do the valid gadget-based stack parity. And another thing I want to mention here is in 64-bit, the erent can be used to the stack parity. The thing is very simple, because every time the SS, ESP, E flag, and the CS, EIP, of course, if you have the error code there, they will push on the stack, right? When the error happens, they will pop. So at that time, if you push the some special value on ESP, on stack as ESP, then CPU just directly installs the ESP as a stack. So that's pretty much very easy way to do the stack parity in future, especially in the 64-bit OS. But here I want to show another approach to the stack parity, because think about the valid code itself could have all kinds of different logic. So for example here, that's very interesting gadget in real software. When you call this function, they do a bunch of things, but the most interesting thing is they will use the first parameter as ESP. So, thank you. So that means first time you call this one, you just put the first parameter as what you want. Then they directly install the value go ESP. So very straightforward to do the stack parity. So after that, you can do a bunch of gadgets. For example, call to the second parameter. Then you call to this kind of valid instruction. They call the stack-based function. So that's pretty much very easy to kick off the stack parity. So even we have all kinds of solutions, but the valid gadget is enough. So for example, my friend Yang Yu last year did the talk in Black Hat. So the basic idea here I want to introduce is think about the JIT engine. So today we use JavaScript, this kind of thing, right? So think about if the JavaScript from the script level you call some function with the parameter, the protocol exactly like some other API. if they do the arbitrary rewrite, they can change the callback or vtable from the memory. Then every time you call the some JavaScript object based method, so eventually they can redirect that to the API call. That means that's the cross-dimension way to call the API from script level. So this is the exact topic he mentioned, like inter-dimension execution. With that way, you never against the value gadget, because all gadgets created by ROP engine. That's all valid code itself. The way just about how you call this kind of API as you want. Of course, probably you need the arbitrary rewrite vulnerability to change the vtable like that. So this is a very interesting topic. So now I talk about some very interesting stuff in Wall 6.4. Because I only have 6 minutes, I will go very fast, but I will talk about the key point. So Wall 6.4 is something you can run the 32-bit code on 64-bit Windows, right? They have a couple different components to support that. So they have 3 different components: Wall 6.4 and Wall 6.4 Win, and also Wall 6.4 CPU. So this one is interesting because this one exactly controls the CPU mode switch. So let's look at that. So before we look at the real code, we introduce the basic concept for logic address transfer to linear address. So basically, that's through the segment and segment table, this kind of thing. So every time, as you know, if you use a segment selector, they have a different definition. For example, here, that's the index, and this is indicates that's in GTL, LDT, and also RPL. So the selector itself can be used to search in the GDT or LDT to get the selector, the segment descriptor. So the segment descriptor have a bunch of definition, but here one interesting thing is the L bit. So this one indicates the code is 64-bit or 32-bit. So this is very interesting. So now in 64-bit Windows, they have a bunch of different they use a bunch of different segments, but here the interesting part is in the segment 33. This one dedicated for 64-bit code. The segment 23, that's dedicated for 32-bit. So this is very interesting part. So if you look at the code, how they transfer mode, for example, we look at this one. That's the query virtual memory. So this one in Wall 6.4, if you call this code in NTDL, in 32-bit NTDL, so they will call into FS offset C0. This one kept one address for the translation, the switch code. So for example, this one point to here. So this is very straightforward. That's a far jump. They use jump to the address with the selector as 33. After that, all code will run in 64-bit mode. So after they finish bunch of requests, they will switch back to the 32-bit. So they use the far jump, also use indirect far jump, switch back. And also beyond that, they also could use the erent queue like that. So because the 64-bit has different implementation, they have a bunch of places in user space to use the erent queue to return to the different address. So then now the interesting thing happens. So think about if the 32-bit code and the 64-bit code share same memory space. Actually not exactly same, but that means the 32-bit code belongs to part of 64-bit. So in 32-bit code, you can access 64-bit code. In 64-bit code, also you can access the 64-bit code, 32-bit code. So that's not exactly same address space, but they overlap. If you do that, that's very interesting because think about the 64-bit code. Compiler compile that as 64-bit code, right? 32-bit as 32-bit. But the problem is when the CPU mode different, CPU will decode the instruction as current mode. For example, if CPU in 32-bit, then you run the 64-bit code. Then if the code, the opcode is correct, so you just run the code as 32-bit. But the problem is the original intention for this code is for 64-bit. So this is very interesting problem. So basically in current Windows, Microsoft implement this kind of thing has has different segment, but all segment can access same piece of code. So that's a big problem, because think about the valid gadget means the compiler compile that as gadget, as code, right? So now you get valid code. Valid code itself compiled by 64-bit, but the code itself totally do different different thing in 32-bit mode. So that's cross mode. That's a problem. Thank you. So basically that's a key point I want to make. Say even you have all kinds of defense part, but this is a big problem, because you cannot say I compile the code with all kinds of policy in 64-bit, in eventually 64-bit binary, but same code section can be could run at 32-bit with total different meaning. So that's problem, right? And also the interesting part here is think about the native 64-bit code itself. Even without 32-bit wall inside, you still can switch from 64-bit code to 32-bit code. That's a big problem. So basically I will skip a bunch of slides because I have limited time. So the key problem here is lots of unintended valid code could exist in wall 64. So from 32-bit you can call a bunch of DLL compiled as 64-bit code. But think about if you switch the mode from 32-bit goes 64, that means all intended code in 32-bit could be available for 64-bit code, maybe different meaning, right? And another big problem here is even native 64 without wall mode, you still can trigger the 32-bit segment, because probably they implement and be ready to use later. But that means in pure 64-bit application, if you get the vulnerability, you can trigger that on 32-bit. Then you still can run 32-bit gadget if they have. So that's very interesting. So last thing I want to mention is we talk about a bunch of approach to defend against the ROP, this kind of attack. So actually the problem is today we still cannot fully against this kind of attack. So from the concept perspective, I want to mention probably we miss some solution like branch transfer access control. So think about every time if the branch transfer happens, we can have the mechanism to guide or check some policy, see this transfer is valid or not. Probably that's the approach in future we can stop the ROP attack, the ROP or drop or whatever similar code reuse based attack. So basically that's all. Thank you very much. So if you have questions, we can discuss offline, because I guess I already run out of time.